For the next example, example 11, I'm actually going to change the problem if you happen to already have a packet. If you would change it to read this way. I'd like to find the volume of the solid bounded by the coordinate planes, so that would be the xy plane, the xz plane, and the yz plane, and also the plane x plus 3y plus 2z equals 6. Once again, I'm going to start with a sketch. And this one I think we can probably even do without the benefit of technology, so let's see what we can come up with here. The coordinate planes, of course, again, are just my 3 coordinate planes. I'm not going to worry too much about those yet. But let's consider this last plane that was described. The x-intercept, if both y and z are 0, would just be x equals 6. The y-intercept, 3y equals 6, so y would be 2. And then the z-intercept, 2z equals 6. Again, if these guys are 0, I would just have z equals 3. So drawing in the traces, that would be the triangle that shows where that plane cuts through the first octant. The plane would go on, of course, behind all 3 coordinate planes, but since the coordinate planes are boundaries, I don't care about anything else, just that part. All right, that surface is actually going to end up being my height function. That's how tall little columns would be coming off the xy plane. And in order to actually accurately describe those, I'm going to want to take that equation and solve it for z. So to get z by itself, I would have 6 minus x minus 3y, and then I'd have to divide by 2. And I'm just going to leave it like that. All right, that'll be the height function. That's the integrand when I do my volume. But I also need the r. I need to know the limits of integration. And remember, r is the part in the xy plane. So you can see right here, the shadow of the shape in the xy plane would just be this triangle right there. There's the r. And again, I'm going to draw my r all over again in just an xy coordinate system. The x-intercept was 6. The y-intercept was 2. And the axes form boundaries. So here's that same region R in the xy plane. All right, to get my volume then, I'm going to set up my double integral. To get a volume, I always integrate my height function. And the height function, the slanted surface here, we've already solved it for z, so we know the height is 6 minus x minus 3y, technically divided by 2, but if it's okay with you guys, I'm actually going to take that divided by 2 and pull a multiplier of 1/2 out in front, just because I don't like to muddy up my whole integral with fractions all over the place. All right, looking at this, it doesn't really matter, but I'm going to go ahead. I think I'll choose vertical rectangles this time, meaning I'm choosing to go in the order dy dx. My lower limit for y would be 0, and the top of my rectangle is on this line. The equation of that line would be, let's see, it's a negative slope for sure, down 2 and over 6, so negative 2/6, or negative 1/3 for my slope, and then the y-intercept would be a positive 2. So that's going to be the top of my rectangle and my upper limit of integration. The dx The x values just go from 0 to 6. And there we go. There's our setup for our volume integral. All right, to evaluate this, I'm integrating dy. So 6 would become 6y. Minus x is also a constant, so xy. Minus 3/2 y squared. And that goes from y equals 0 to y equals -1/3 x plus 2. Dx is still hanging out there waiting its turn. All right, I'm going to need a little space, so let me come down all the way to the left here. Plugging in the -1/3 x plus 2 for each of these y's. Just do that right now. Just like that. And then plugging in y equals 0, there's a y in each term, so those are all going to become 0. Don't need to write them. And I have a kind of a big ugly integral, but it's nothing that a calculator minds doing at all. So you can plug that into your calculator to finish it off. And when I did, I actually got 6 for a final answer. All right, so that's volumes where the base was always in the xy plane. The next and last thing we're going to do in this very long section 13.2 is talk about volumes between two surfaces, where the base isn't necessarily sitting right on the xy plane. So I need to use a double integral to find the volume of a solid between two surfaces. Once again, I'm going to kind of try and do a couple of generic surfaces. Maybe I have an upper surface here. Z equals f of x and y. And I also have a lower surface. Z equals g of x and y. I'm interested in finding the volume of the solid between those two surfaces. In order to do that, I'm going to once again set up a double integral. And just like before, what I want to integrate is going to be the height function. But since the height doesn't go all the way down to the xy plane, or z equals 0, it just goes between these. If you imagine a little column going from the top to the bottom here, the height of that column would just be the upper z value minus the lower z value. So to get my height, I'll take the top surface, f of x and y, and subtract the bottom surface, g of x and y. If you think about it, technically we've been doing that all along. If I go back to the last diagram that we drew, where the height function was just f of x and y, the bottom here, because it's in the xy plane, would actually have equation z equals 0. So technically speaking, I was subtracting a 0. We just didn't talk about it because we didn't need it. All right, so there's my new height function. Top minus bottom. Now, my limits of integration. To get the limits of integration, what I need to do is think about where these surfaces intersect. There's this region of intersection between the two surfaces. Imagine taking that region and projecting it down into the xy plane, kind of like so. that projection of the intersection into the xy plane is going to be your region R. And you're going to integrate over that region R, dA. Again, dx dy or dy dx, whatever works better for a particular situation. All right, so let's try a couple of problems like this. In example 12, we're looking for the volume bounded by the surfaces. Z equals x squared plus 1, z equals y plus 1, and y equals 1. Again, just two variables, meaning I have a cylinder. There is no y, so it's parallel to the y-axis. These are just going to be planes. We'll talk a little bit more about those when we're ready to draw them. I'm once again going to attempt to make the picture first by hand, just for a little practice in visualizing, and then we'll look at a couple of technology solutions to graphing these things. So here's my three-dimensional graph. This surface is z equals x squared plus 1, just a parabola shifted up 1 in the xz plane. So that's 1 right there. Got this parabola, and then I'm going to pull it along parallel to the y-axis. Kind of like that. So there is my cylinder, z equals x squared plus 1. The plane y equals 1 is just a vertical plane parallel to the xz plane. And just to make my life easy, I'm going to assume that I magically stopped here at y equals 1. And that kind of cuts off the end here. So it puts an end cap, if you will, on my shape. The z equals y plus 1, that's going to be a plane parallel to the x-axis. Y plus 1 is going to have a z-intercept of 1, so it's going to start at the same point here. And then it's just going to kind of lay a slanted plane, almost like a lid, a slanted lid on this thing. As it cuts through, it'll kind of curve right along with our surface, creating kind of a slanted parabola as a top. And I know this isn't a perfect picture by a long shot, but just kind of trying to get a feel for it right now. So that's my slanted plane, z equals y plus 1. The curved bottom here is that cylinder. That was our z equals x squared plus 1. So just to help me keep track, it's that one, it's that one, and this is the y equals 1. All right, if my attempt at a picture isn't too convincing or you'd like to see maybe a little bit better picture, let's take a look at a little bit of technology here. Here it is in Maple. We've got our cylinder here, the parabolic cylinder. Here's that slanted plane y plus 1, and here's that vertical plane y equals 1. So you can see the same thing. One nice thing here is if you kind of look at it from the top, you can really see that parabolic lid that I was trying, only somewhat successfully probably, to draw in our picture. So there it is in Maple. And here it is in Geogebra. Again, you can see the parabolic cylinder. You can see the vertical plane y equals 1 and the slanted plane z equals y plus 1. This down in here, this little tiny piece, is what we're actually trying to find the volume of. And I can rotate that a bit, look at it from top down to see that parabolic piece, that parabolic lid again. Again, I really encourage you to play around with whatever technology you have available at home that will help you to visualize these kinds of things. All right, so if we're kind of convinced that we know where we're going with this, let's set up our volume integral. Double integral always of the height function. All right, for the height, I need to go top minus bottom. And this is where the picture really, really helps. If you think about this shape, it's pretty clear that the top is this yellow slanted lid. That was my equation y plus 1. And the bottom is this sort of pink stripe piece. It was that parabolic cylinder, the x squared plus 1. And you know what, actually, I'll leave the dA for right now, but I think I'll fix that in just a minute. Let's talk about R. The region R is going to be the projection of this yellow parabola down into the xy plane. So it's going to kind of look like this. In order to draw that accurately in the xy plane, what I'm going to do is notice that that parabola is really the intersection of this plane, y plus 1, with this cylinder, x squared plus 1. They're both equal to z. So to get their intersection, all I really have to do is set the z's equal to one another. Which just gives me y equals x squared, a really nice simple equation. And then y equals 1 is what formed the end of it. I probably didn't go up quite far enough here. I should have gone all the way out to the 1. We'll pretend I did. We do know that y equals 1 is the top here. So there's our region R, redrawn in just the xy plane. Let's go with vertical rectangles to get our limits of integration. And since I'm doing that, that really commits me to dy first and then dx. Y, bottom to top, goes from x squared to 1. And then the x values would be those intersection points. If I set those equal to one another, x squared equals 1. X is plus or minus 1. And that gives me my limits of integration on the x. All right. So, what have I really got here? When I subtract, these 1's are going to end up subtracting away to 0. So I have y minus x squared dy dx. And integrating dy will give me a 1/2 y squared minus, that's a constant, x squared times y. And that goes from y equals x squared to y equal 1. Plugging in the y equals 1 first, I would have 1/2 minus x squared times 1, or just x squared. Subtract, plugging in x squared for y. X squared squared will make that a 1/2 x to the 4th. Minus x squared times x squared is x to the 4th. And you can simplify that a little bit if you want to, but whether you do or whether you just plug it into your calculator right now, you should get the same answer. Let's see, when I did it, I got 8/15 for that volume. All right, we will pause there and finish the very last example in the finally last video for this section.